And yeah, so hello everyone. Like Suman said, this is going to be my last lecture, and Janki will follow with 2 tutorials after this. So if you have any doubts regarding any of the things being covered in the lecture, of course Janki will try to cover as much as possible. But you're also free to write to any of us after all of this is over. I mean, in fact, you're looking for a reference or something, you're always free to ask us, and we can engage in a conversation after this lecture series is over. So I just wanted to let you know. And again, like Suman said, you're free to stop me anytime during the lecture, and I'll stop and ask you again. But you can always raise your hand and say, "Look, I want a question. I want to ask a question right now." Okay. So let me start today. This was the view graph that I showed yesterday. This was, if you remember, the evolution of spin temperature, the dot dashed line. Spin temperature starts close to the common temperature of CMB and matter at very high redshift. It deviates significantly from the CMB temperature and approaches matter temperature. You can easily see that at some point for a range of redshift. And then it approaches the CMB temperature back again. We want to know what the implication of this is and various other things, physical processes I'm going to introduce in today's talk for the observable. To know the observable, first have to introduce a few things. And this could be a bit of a repetition in what has already happened. But let me do it in any case, because we all use our different language, and I'll spend a bit of time explaining the problem of radiative transfer. And to simplify it a bit so that I can give you a sense of the most relevant processes here, I will do it for the static medium. I mean, the real medium is actually expanding. It doesn't change the physics much, but some of the expressions change. So what I have done is I have written here an equation for line emission in a static isotropic medium. So this is the equation for the specific propagation, the evolution of specific intensity along the line of sight. So ds, which on the left hand side, s is the line of sight. So you are sitting at S2, and the absorption, the signal is coming from everywhere between S1 and S2. S1 is some further off point. So the first term on the right hand side, so you can see first thing about static media is the intensity is conserved of light ray unless the photon is either emitted or absorbed. So that's the first thing. I nu by ds would be 0 if not for the right hand side. So it is not true in expanding universe. The intensity changes as 1 by z cube actually there, but it doesn't make any big difference in this equation. So the first term on the right hand side is there is a minus sign, so that is absorption. And you can actually see absorption is there is a photon energy there, h nu 1 2. Absorption will be proportional to n1. If there are atoms in the ground state, a photon comes and is absorbed and it goes to the excited state. That's the first term. The second term comes from induced emission, and something we discussed yesterday and we'll discuss today again. So the absorption can either be dominated by the second term or the first term. So absorption can be positive or negative. When absorption is negative, that's what's called maser or laser, right? And I'll come back to that point again. So the first term is what is called absorption. The second term is called emission, right? It's a simpler term. The emission is purely governed by the fact that you have a spontaneous decay of the line. So you have a hydrogen atom, hyperfine structure in its excited state, and slowly that state decays. And what we see as a result is what emission is. Phi nu is what's called response function. And again, I'll refer you to Rybicki and Lightman for definition of response function. Generally, it is normalized to unity, integrated over all frequencies. And it takes various forms. For expanding universe, it's much simpler. If you have natural decay or you have Doppler width, then phi nu can have more complicated forms. But I will not even discuss what phi nu is here. I'll not need to from what I'm going to say next. In the next line, I've just given relation between B1 and B2 and A to 1, and you would expect these relations. I mean, A to 1 is missing here. I'm sorry, in the definition of B to 1. My apologies. Right? There should have been an A to 1 here. So what you need is you have to define, for studying this entire process, you have to find one thing, that is the emission, and all the other absorption A and B coefficients are fixed by that process. That is basically the point about the line next to equation 17. If you want to solve it, we may want to know what N1 and N2 is. And what we do is something we did yesterday. We assume that N2, the relative population of the two levels, are given by this relation, equation 18. And you realize I have defined a spin temperature here. Ts, the same spin temperature I was talking about yesterday, right? But there is a reason why N2 and N1 were defined in the way they are. In yesterday's talk, I told you that you can actually compute the detailed balance equation without defining these equations this way. But you will notice now why equation 18 and or what I defined yesterday, why these definitions are used. So first, let's define alpha nu as the net absorption coefficient, which can be either positive or negative. Remember, and emissivity, J nu. First thing you notice about alpha nu is, and I have given it in equation 20, that it is positive in this case. Why is it positive in this case? I said it can be negative or it could be positive. It is positive because of equation 18. Equation 18 assumes we are in some form of thermal equilibrium. And that was the reason TS is defined in this way, right? And notice alpha being positive means there is no laser. When Ts is equal to matter temperature or CMB temperature, it's clear, but Ts could be anything. But so long as N1 and N2 can be written in this form, alpha nu is positive and there is no maser or laser in this case. And it's actually a very clear thing that in thermal equilibrium, you do not have masers. And you can, from the expression of alpha nu, now you can see why to get a maser, the second term has to dominate the first term. But for that, you would require the number of atoms per degeneracy state in the excited state to be more than in the ground state, right? N2 is close to 3 times N1, that much is clear, right? But it's still a little smaller than 3 as equation 18 tells you. So that prevents amazing action from happening. And in thermal equilibrium, it never happens. You'll have to go out of thermal equilibrium for that to happen. That answers partly the question I raised yesterday. But one important thing here, which should be noted by everybody, is that it doesn't mean stimulated emission is unimportant. If you look at the expression for alpha nu, you immediately notice that the second term in the definition of alpha nu, which is proportional to N2B21, nearly cancels the first term, N1B12 actually. You can write down the expression and easily verify this is indeed the case. It nearly cancels. In fact, in equation 20, you have this factor H nu 12 divided by KTS, which comes from the fact that there is a near cancellation of these two terms in the definition of alpha nu. H nu 12 divided by KTS is actually very, very much smaller than unity actually. This term has come from expanding the exponent in equation 18. So 1 will cancel, what remains is H nu 12 by KTS, which is extremely small. Remember, H nu 12 by K was 0.068 Kelvin. And Ts, from what you have seen, is matter temperature, CMB temperature, is hundreds of times larger. So if somebody asks you about stimulated emission, you don't have to refer to a laser or a maser. You can always refer to an H1 line, hyperfine line. In H1 hyperfine line radiation transfer, stimulated emission plays an extremely important role, but it still doesn't cause a maser because the processes happen close to thermal equilibrium. It's a very important point and I want you to think about it. But I'll move on and we can discuss it later on during the talk. What you define further, something called emissivity, what we define further is what's called source function. It's a matter of definition, but it plays an important role. So what you do is you take alpha nu from equation 17 by defining it the way I have defined it here, divided the whole thing by alpha nu. That gives you a source function. A source function looks like a black body at the temperature Ts. That was the reason it was defined the way it was. And I have always assuming, as I have said, H nu 12 by KTS is much, much smaller than unity. Otherwise, source function would be a more complicated function, but still tractable. So equation 19 defines source function. Equation 20 gives you alpha nu, the net absorption, which is the first term weighted down by H nu 12 by KTS, which is basically stimulated emission, which kills most of your absorption. So, and in fact, you understand what really is happening here. If a photon is coming from behind a hydrogen atom, and you absorb a fraction of them by going from ground state to the first excited state, and that would be what you'll call absorption. If you have, there are 1,000 such photons which have been absorbed, almost 999 are given back to you along the same line of sight by the inverse process. And that's what the definition of alpha nu is telling you. So absorption of this line is in a very weak. I mean, emission is weak enough, but absorption is even weaker. So once I define source function and I define alpha nu, I can further define differential optical depth, which is defined right here, d tau nu equal to alpha nu ds, and integrated from the point of emission to the point of observation. This gives you the optical depth of the medium. This equation now, equation 21, is fairly straightforward, and you can actually integrate it quite easily. What we do normally, and something I'm going to do very soon, is to define something called the brightness temperature. Brightness temperature, again, at small frequencies is defined by writing I nu as 2k TB divided by lambda 1 2 square. I mean, I can always define it like that. Source function, remember, was already in this form, right? So I can cancel out lambda 1 2s from everywhere. And once I cancel out, so this cancellation is a little harder, for instance, when I'm in expanding universe. Static medium is straightforward. I get equation 22, and equation 22 is generally what we normally solve, but we should know what are the intermediate steps. And that was my aim so far, to tell you what the intermediate steps are before you reach equation 22. Equation 22 is a fairly straightforward equation to solve. I can solve it between 2 points along the line of sight, an initial point and the final point, which is the observer. I'm going to write down the solution for tau nu much smaller than unity. And this is justified by what I'm going to do later. Tau nu is indeed much smaller than unity. And if you notice, Janki has given you notes, and she has discussed tau nu, and you can see it's much smaller than unity for all cases of interest for us. So tau nu is much smaller than unity. And we also assume that TS is roughly constant at the source, which is generally a good assumption because it's a line radiation. Most of the radiation emanates from a single point or close to a single point for a observed frequency. So you can pull that TS out. TS doesn't evolve so fast. This gives you equation 23, and equation 23 is a master equation we use again and again. Let's look at what this equation is. This is the observable quantity. What we observe is the difference in brightness temperature between point S1 and point S2. This is the only observable quantity we have. Because if at S1 there is something, and here in this case, in the high redshift universe, at S1 the brightness temperature is given by CMB temperature. So what we measure is the difference between the brightness temperature at the present minus the brightness temperature at S1, but actually in the expanding universe, you have to scale it down by a factor of 1 plus Z. This is what is the observable quantity. It is a difference between two numbers. That's what we observe. We do not make absolute observation. We compute a difference between two quantities. Of course, you can say maybe TB is 0. Suppose TB was 0. There is no background, right? Then you can see put TB equal to 0. Then delta TB is just TB at S2, and that is tau nu TS. And you can also show that if tau was very large, if it tended to infinity, TB will actually extend to TS, or the source temperature and the brightness temperature, they have the same value. That happens when tau nu is extremely large, and you can actually look at it. You can solve equation 22 and not take the limit of tau nu much smaller than unity. We'll be dealing throughout with equation 23. We obviously have something in the background. In the background, you have CMB. CMB falling from behind on a parcel of gas. And our observable signal is the difference between the brightness temperature that we observe minus the CMB temperature that we actually see at the current location, which is not obvious from here because I've not taken into account the effect of expansion. But this is the master equation we use in all radiative transfer problems. Something akin to this. And in the next view graph, I'm going to actually write down the correct equation as applicable to the expanding universe. So you can see delta TB is equal to TB minus TCMB. Now they're computed at the same point, equal to tau. Remember the tau, 1 plus z factor takes care of the fact that I have to scale it by 1 plus z. TS minus TCMB. So now I have replaced the background with TCMB. This is what the solution is, and this is what the observable number is. One can compute this tau for parameters in cosmology, and Janke has given you a detailed calculation of this in her notes, so you should be able to follow it, right? Tau is proportional to 1 by Ts, so Ts should be taken out common from equation 24 to cancel the Ts. And once you cancel that Ts, you get equation 25, and equation 25 is the one which is of great interest to us, and we shall dwell on this for a while. What is equation 25 telling us? It is telling us that if Ts is much, much larger than TCMB, it's possible, then the observable signature is close to 26 millikelvin for neutral fraction of unity. So I have divided it by neutral fraction. H1 is a neutral fraction. So if the entire gas is neutral, I expect to see a signal of around 26 millikelvin at a redshift of 10. That's the point. It's clear to you, right? Roughly. If the neutral fraction is half at that redshift, I'll get half the signal, around 13 millikelvin. So the typical number to keep in mind if you want to see the signal in emission is between 10 to 20 millikelvin. Good point, right? So that's a number one should keep in mind, 10 to 20 millikelvin. By the way, it answers one question which I raised yesterday, but I did not address. And I'll go back to that view graph and I'll come back again here. Last point, self-absorption and induced emission, right? I asked the question that in this view graph, we have, and in yesterday's lecture, we took into account 3 processes, all driven by external fields. You have a hyperfine level. So you have a de-excitation rate by CMB, which is an external field, by collision external. Well, they are internal to the process, but not to the level population itself. De-excitation by Lyman alpha, again external. Point is, why don't you talk about things which are internal? What about photons that are emitted through a natural process? Why are those photons not self-absorbed? Do they not cause induced emission? Well, they would if the optical depth of the medium was large. Then there is a great chance that they will get reabsorbed, right? And self-absorption will play a role. Now that plays a very important role in studying one problem only that I know of in astronomy. That is when we were trying to study the center of our own galaxy. The optical depth from H1 only approaches unity when we look towards the center of our galaxy. Otherwise, it's always smaller than unity, right? And for the reasons I have told you already, that optical depth is small, partly because the emission itself is weak, but partly because the induced emission plays an important role there. So there is only one setting I know of where self-absorption, induced emission by photons which are produced through this process itself is important, right? So it is not important for our case, and tau is much smaller than unity. And you can see the emission itself corresponds to just a few millikelvin. Compare it to CMB, which is at least a few Kelvin, even at redshift of 0. So the fourth point here, do they play a role in our problem? No, they don't. They do not play a role, not for our problem, but you can actually think of a problem where they may play a role. It might happen. So there could be settings in the universe where they may play a role. For instance, if we have an H1 cloud, which is very dense, and it has a column density, the highest column density we have ever seen from an H1 cloud so far is close to 10 per 22. But if it was larger by a factor of 3 or 4, we might be actually in the limit in which we have to rethink the problem that we did yesterday. We'll have to take into account self-absorption in the problem. So one solution of equation 25 is clear to you. If I were to see the gas in emission, the brightness temperature of the gas would be around 10 millikelvin, very small compared to CMB temperature. How about absorption? Can I see the gas in absorption? Absolutely, I can see the gas in absorption because TCMB can be larger than TS. And I showed you yesterday that it is indeed possible in the simplest case we discussed, which was a pre-dawn signal, the TCMB is indeed more than TS. TS is close to matter temperature and TCMB is larger than that. So we see the signal in absorption in that case, right? So you replace TS with TM here and you can see the signal in absorption. So it is possible to see the signal both in emission as well as absorption depending on what the relative strength of TCMB and TSR. Of course, it's possible, and I'll come to this point a little later, that TCMB is replaced by something else. TCMB is only for us a field that is behind the parcel of gas. If there is something else behind also, there is radio emission for some other reason, then TCMB has to be enhanced. You can enhance it by that factor. So you may be able to see it in absorption or emission depending on what other complicated processes are taking place. I'll give a very brief summary of what we actually see, and I'll show you a view graph. In the next view graph, I'll show you a figure. So for the range of redshift between 100 and 1000, delta T is roughly 0 because TCMB and TS are the same. If they are the same, the signal goes to 0. That is very clear from equation 25. Between roughly redshift of 20 and 100, and these are the typical numbers, which are not entirely correct. I mean, I'll show you an exact figure. Delta T is 0 because during that period, TS is equal to matter temperature. And matter temperature is less than CMB temperature. So you should see this in absorption. Just forget about the third part during reionization, what happens. I will do it in greater detail. But what happens after redshift of 20? It goes back to CMB. Remember the TS? That means the signal will again go to 0. This is how it looks like. What I have done is I have plotted the observable quantity as a function of observed frequency. Observed frequency, remember, is the frequency in the rest frame is 1420 megahertz. And observed frequency is a factor 1 plus Z below 1420. So if I'm talking about frequency of 50 megahertz, for instance, right? We are talking about redshift of roughly 70. I hope you get that point, right? So I have actually plotted not as a function of redshift, but as a function of observed frequency. This is the observed signal and this is pre-dawn. This is the era where I have not assumed anything about epoch of reionization yet, but there is a signal which is sitting out there at very low frequencies, which are between 10 to 20 megahertz. And I've given you a range of models here to motivate in some way the range in which it can occur. That range has shrunk since because this paper was written long ago and the parameters, cosmological parameters were not as well constrained as they are now. But fact remains, we are talking about a signal which is fairly deep, right? Around 0.5 to 0.6, between 50 to 60 millikelvin. That is a signal that you can see in absorption during the pre-dawn era. That is a basic message. But there is also another message here. At large frequencies, which is closer to you, the signal goes to 0. So even though there is H1 gas, imagine at equation at redshift of 70 megahertz, the signal goes to 0. There's a lot of H1 gas here. Redshift of frequency of 70 is still close to redshift of 20. And the universe is expected to be quite neutral at that, but the signal is 0. So some other processes must now happen to make this signal observable again. Otherwise, this is all that we'll see. A signal at fairly low frequencies, around 20 megahertz, and nothing at larger frequencies. And these are the following three processes that happened during the cosmic dawn. So after fairly long introduction, like almost 2.5 lectures, like I have finally come to what happened in cosmic dawn, and now we have all the machinery to solve this problem. So what happens is the first structures form around redshift of 30. And you have been told this, you're studying structure formation as a part of this course. So you know that the first structures, nonlinear structures form around redshift of 30. These structures have masses in the range. I have put a typical number, 10 to the power 6 and 10 to the power 9. But it could have a different range. I mean, this range depends actually on whether the halo that forms is cooled by molecular hydrogen or atomic hydrogen. If it is molecular hydrogen, 10 power 6 is okay. If it is atomic hydrogen, the typical lower mass would be around 10 power 8 solar masses. So this range is in itself a topic of discussion in the literature, and we have never really fixed it. I mean, it could be around 10 to the power 6, large number of small halos, or if it is atomic cooled, it could be larger halos like 10 to the power 8 or above. But we expect these structures do form at around redshift of 30. Slowly they start forming, and more structures form as the universe evolves. What bearing does it have on the problem that we are studying? These structures emit continuum radiation in a vast wavelength range, actually. So this is continuum radiation. There are stars in these objects, remember? So stars emit in a huge range. I mean, they don't emit in X-ray, but binary stars do, and our galaxy has enough emission in it. The three radiation fields of interest to us are the following. We've already seen the importance of Lyman alpha. Lyman alpha, of course, plays a very important role. And you have seen what role it does in mixing hyperfine levels. What is called Lyman alpha in the parlance of the cosmic dawn epoch of reionization field is actually not feed photons at Lyman alpha, but actually between Lyman alpha and Lyman beta, right? So Lyman alpha and Lyman beta is, you have seen the hydrogen levels, it's just a level above. So if a photon is produced between Lyman alpha and Lyman beta, it actually free streams into the medium and loses frequency unless it comes very close to the resonance of Lyman alpha and that gets absorbed. That's what really happens. And in her notes, Janki has given you typical numbers of how far it can free stream a photon between Lyman alpha and Lyman beta. So this is a photon that is produced but travels long distances, because like typical continuum photon will be between Lyman alpha and Lyman beta and can travel long distances before it's absorbed by resonance scattering into the medium. And as you have seen, this mixes H1 hyperfine levels and it does a pretty good job of it. The cross, if you remember, the rate of this was larger than other rates at redshift of 20, and that's what I discussed yesterday. The second radiation, which is absolutely required because after all we are studying epoch of reionization, is radiation that ionizes. Lyman alpha cannot ionize hydrogen atom. You see, it doesn't have enough energy. For ionization, we need photons of the order of 13.6 electron volt or just above. The cross section for ionization is a pretty sharp function of about threshold. At threshold, it reaches a maximum, and then it falls roughly as 1 by nu cube after that for larger frequencies. So photons which are pretty close to 13.6 electron volts are preferentially absorbed close to the structure. And at redshift of 30, if you were to find the mean free path of such photons, it's close to 1 kiloparsec co-moving. So it doesn't move a lot, right? I mean, I've just computed at 13.6, but initially it gets absorbed, and then the ionized region, because the universe dilutes, it expands. That is in itself. So these are photons which are absorbed very close to the structures, where forming structures, and they have small mean free path, and they cause ionized regions around these forming structures. So this is ionizing radiation. So there is Lyman alpha, there is ionizing radiation.
Shiv, there is a question from Antara there.
Go on.
Yeah.
Go on.
Sir, you have said that the masses of the structures will be 10 to the power 6 to 10 to the power 9 solar mass, and it depends only on the atomic cooling or molecular cooling. Does it can depend on the cosmology? Like if you assume the lambda CDM or any interaction, then...
Sorry, can you please repeat that last part of the question? I couldn't hear you.
I am asking that if the masses can depend on the cosmology.
Yeah, they do depend on cosmology. They depend pretty sensitively on cosmology. But I have lambda CDM model in my mind when I say it. So for the lambda CDM, this is the typical range. Can you again specify your question? What exactly do you have in mind?
I am asking that if we consider any dark matter interaction, then if the power spectrum suppresses than the lambda CDM, then this M mean can depend on that suppression, or...
Absolutely. So the whole point is, if you suppose, like I have studied some of those models myself. So So suppose you were to suppress power at these scales, right? Then they will not be able to form easily. So you see what happens is in a lambda CDM model at a redshift of around 15, the smallest mass that roughly forms around 10 power 6, it's a 2.5 sigma event. Okay. If you suppress power, that is a higher sigma event actually. So mass can form, but it will form with less probability. So the structure can form. It's not that it cannot form because you have cut off power, but you have not made it zero. So if you take a different dark matter model, a dark matter model in which power is suppressed at small scales, then the spectrum of masses that will form will change. Right? So that absolutely, and we have studied it actually in one of the papers I worked on, and it leads to meaningful observables at the end. So, for instance, if you form fewer objects, they will also be more strongly clustered. So the H1 signal, the ionized region would be larger in that case as compared to the lambda CDM case. So yes, absolutely. To answer your question, I don't want to go into a lot of details on this because I do not have supporting view graphs. I mean, we did not prepare a talk on the talk of reionization part actually. But yes, to answer your question, yes, absolutely. If you have a different dark matter model, it will change. So the mass range for if you suppress a 10 to the power 6 a lot by some reason, then it may not even be 10 to the power 9. It could be even larger than 10 to the power 9. But if it is larger than 10 to the power 9, then it's a higher sigma event. I mean, so it's possible. I just wrote the typical numbers here. So does that answer your question? Are you okay?
Yes, sir. Thank you, sir.
Yeah. Okay. Yeah.
Yes. So Shiv, I have another question regarding
please.
Lyman alpha emission. So Lyman alpha is produced by the stars and I mean the structures that produce, right? And these structures are produced in high density regions where there is a more neutral gas.
That is correct.
So now my question is whether Lyman alpha can free stream through such a large neutral medium or not.
I'll answer your question actually. Let me.
Okay, sure.
I'll just show you a figure which I showed yesterday. I'll come back to this. Okay, this is Lyman alpha, a cross section. Okay. So
Yes.
if I produce a photon which is very close to the resonance, it has a very, very small cross section, right?
Correct.
But suppose, and you see delta nu d is roughly 1/5 of the 10 to the power minus 5 times. So delta nu d by nu alpha is roughly 10 to the power minus 5.
Right.
So it's a very small number. If I produced a photon which is 40, suppose 80, minus 80 or plus 80 on either side, red word or blue word of the Lyman alpha, it will free stream into the medium.
Okay, right.
So you see, when you say free stream, you actually have in mind the resonance. This photon, the one which is produced close to the resonance, of course, do not free stream into the medium, is trapped locally.
Correct.
Okay. But in continuum radiation, I am producing photons which are redward side as well as blueward side, right?
Right.
So if you are just 80 times or 100 times, you can see the cross section. Cross section is fallen to less than 10 power minus 20.
And these other photons like 100 or 80 photons can also do the hyper fine, I mean the inversion.
Only after redshifting.
Oh, okay. Yes,
So you
that's
see
right.
what happens is first when they escape into the medium. So the first problem is they are formed, like you said, in a dense region. First they have to escape the dense region.
Correct.
When they escape the dense region, so suppose you have a photon right here, which is like 100 times, which is removed by 100 times delta nu d from the resonance, right? This photon escapes into the medium, but what will happen to this photon? It will redshift.
Correct.
Its frequency will get closer and closer to the resonance. So once its frequency comes close to resonance, somewhere here maybe it can, when it's like cross section has come to around 10 power minus 17, it will get absorbed then.
Right.
So you get my point. Yeah, it is possible. I mean,
Correct.
so you see, when we talk about Lyman alpha, we mostly talk about the resonance. But you see, that's why I showed this curve.
Correct. Right. That's right.
Dominates near cross section, but near resonance, but it falls to a very small value actually, far away from the resonance.
That's right. Yeah.
Okay. So that's what's happening. Photon is born. It escapes the dense structure where it is formed. It redshifts, come close to the resonance, gets absorbed.
Correct. Right.
And this distance is not very, for this figure, the distance is not very large, but it cannot be delta nu D by nu alpha, it's 100 is not much actually. It's very small. You
Oh,
can be
right.
close to Lyman beta, right?
Mhm. Correct.
That is around 10,000. Then this number is more than 10,000 actually.
Right.
Okay.
Right.
It's even smaller.
Correct.
Okay.
Yes.
So yes, it can
Thanks.
form in a dense structure and escape.
Mhm.
That's the point.
Right. Thanks.
Okay. All right. So are there any further questions at this stage? No, I'll just go on then. Right. And please stop me anytime. There are any questions. Right. Please do not hesitate. So photons of energy which are greater than 200 eV now, they are very complicated. They are hard to deal with. So I've said ionizing. Ionizing also heats the medium, but its major task of these photons is to ionize. It heats the medium to around 10 power 4 K, and it can be shown. It always ionizes, heats everything to 10 power 4 K. It can be shown. Heating is a little more complicated. Heating means ionization doesn't happen that much. So if you have photons of energy which are greater than 200 electron volt, typically, their mean free path is much larger than 13.6 electron volt because the cross section of absorption is down by a factor of 1 by nu cube. So you can see 13.6 divided by 200 raised to the power 3. That gives you a much larger number, right? So these mean free path of such photons could be tens of megaparsecs. And again, Janki's note, she has actually given you these numbers. So they get absorbed far away from the ionized region by photoelectric ion. So they also generate heat by ionizing. But that is a more complicated process because there are far fewer of these photons as compared to the one close to 13.6 electron volt. And I'll briefly touch upon these physical processes. So first, again, Lyman alpha mixing, something I have talked about again and again. You remember, if Lyman alpha mixing does not happen after the pre-dawn phase is over, TS is equal to TCMB. So TS has become equal to TCMB, and without this Lyman alpha mixing, cosmic dawn or epoch of reionization is not even observable. That's a very important point actually. That once TS has gone to TCMB, I have to take it out from there and push it again in some other direction. I have to make TS closer to TM again. If that is not possible, then the signal is unobservable. So without Lyman alpha mixing, neither cosmic dawn nor epoch of reionization, none of it, the H1 signal is not observable. So this plays paramount role in what we are going to observe or what we are observed so far. Lyman alpha mixing is very, very important. Second, again, very briefly, the mostly neutral gas during cosmic dawn is heated by actually two processes. Okay, UV hydrogenizing photons, they ionize the medium, I said it, and the ionized gas rate ratio 10 power 4, you can show it, and I'll urge you to show it, that this temperature is nearly independent of particle density, intensity of photon field, and it's about 10 power 4 K, but not of great interest to us because this is the temperature of the ionized gas, something we do not see. X-ray photons, they partially ionize the gas, and I'll very briefly tell you how this actually works. So what happens is a photon comes, like I said, it escapes the ionized region, it goes far away, and it gets absorbed finally. What happens when it gets absorbed somewhere? Amount of energy, the rate at which energy is pumped into the medium is proportional to the right-hand side. It's actually equal to the right-hand side. So this depends on the sigma, the cross-section of absorption. It depends on the number density of photons per unit frequency interval, which are out there in the medium. And it depends on the difference of frequency between. So part of the energy of the photon goes into ionizing the atom. The rest goes into the electron that is emitted, and that's what is heating. So this is the rate at which the energy is being pumped into electrons, and electron, I told you before, will share the energy with everything else. So, but you see that electron that is emitted has also and also has energy much more than the threshold. Suppose you have a 200 electron volt photon, which is absorbed in the medium. New threshold is just 13.6. So the remaining energy that has gone into the medium is still more than 13.6 electron volt. That secondary photon can again ionize. It is a complicated problem. This problem has been studied in a couple of papers in 1980s and in 2000s, but I still believe that it needs to be studied in a little more detail actually, because I don't believe that a time-dependent problem of this kind has been studied as well as it should be. But from what we know from those papers, nearly 15% of the total energy that is gained heats a gas. And the ionized level of the gas doesn't rise about 10%. So you cannot ionize the gas this way. The ionization of the gas remains below 10%. 15% of this total energy goes into heating the gas. So the net effect of heating by X-ray is to heat the gas rather than ionize it. And that's exactly what we wanted. We wanted neutral gases to be heated, not ionized. Ionization is done by UV photon. Neutral gas heating happens from these X-ray photons. Photons which have energies more than 200 electron volt. But depending on the model you have in mind, it could be 1 keV, 2 keV. We study all kinds of models when we do this because there is a fair amount of uncertainty about these processes. These first structures, how this emission takes place from first structures.
So this X-ray heating can also affect the structure formation, right? Because now neutral gas would be slightly higher temperature as compared to the lower. So
Yes.
the potential well would be, I mean, it will not. I mean, the gas will be supported by pressure rather.
That is correct.
Mm-hmm.
That is actually we do take that into account in the formation of structure that the gas temperature has actually increased, right?
Yes.
But if you take into account the fact that suppose it's hydrogen cooled gas, then the first structure that forms around 10 to the power 8 solar masses.
Correct.
And 10 to the power 8 solar mass has a virial temperature of close to 10 to the power 4K.
4K, correct.
The heating from X-ray is rarely about temperature of 1000 degrees.
Okay, correct.
So in fact, it does not prevent the formation of those structures.
Right.
But if I were to form structures for molecular hydrogen cooling, then it will affect.
Correct.
So the correct answer to your question is X-ray heated neutral gas does not prevent the formation of structures of masses 10 to the power 8 or above.
Correct.
But below, 10 to the power 6, yes, it will. So that is why it is a complicated process. If you have molecular cooled halos and you start heating the gas in the surrounding, you switch off the formation of those halos too.
Correct.
Right?
Yes.
So when one does simulation, one sometimes take that into account. I have done semi-analytic modeling where I did take this into account.
Correct. Yeah. Thanks.
And ionized regions also, they are 10 to the power 4K, right?
Right.
So in those regions, you can't form structures of even 10 to the power 8 Kelvin, 10 to the power 8 solar masses, only higher ones can form from the ionized region.
Correct.
So there is a feedback. You're absolutely right. There is a feedback and it's important.
Yes.
Compton scattering of laminar photon something that has created a lot of confusion in the literature, which hasn't gone away entirely. That you can Compton scatter laminar for photons in electron rest frame. Compton laminar for photon can come just hit, and I shouldn't have said electron here. I should have said the atom. It can just hit the atom, and in the atom's rest frame, it gains energy from the photon. Can it heat? Well, but in the lab frame, we should look at this process as an equilibrium process. And as an equilibrium process, it can also lose energy when you take into account the balance of the two. There are two kinds of starting conditions you can have. In equilibrium, T alpha is Tm. You can start with initial photon distribution, which can correspond to either T equal to alpha or T alpha equal to infinity. And you can figure out what those two things are. Even then, the net energy exchange is generally small in both cases. So Compton scattering of laminar for photons of neutral atoms does not play a very important role in heating the medium, right? And I will not say anything further. It's a very important point, something we keep studying. I'm involved in studying this process currently. But it's pretty complicated. I don't want to go into any further details of this. For the rest of the talk, of course, I'm going to assume that all the heating models are based on the photoelectric heating by X-ray photons in the neutral gas. Here you have a first glimpse of what might happen when you heat in addition to mixing. Let's pay attention to this curve. You have a red curve, right? In the red curve, what you have done is you start heating. Actually, one should not, this is around 20 megahertz, the trough that you are seeing in negative comes from pre-dawn era, you know already, right? I am switching off these three radiation fields, right? X-ray heating, laminar alpha mixing, and UV ionization, roughly around this redshift. It's up to me. I mean, this is based on models which I worked on long ago, when the epoch of reionization was slightly higher. But now it is pushed to higher frequencies, but the process is exactly the same. So if there was X-ray heating, then you have a trough. It goes into an emission peak. From trough, it goes to emission. And as the universe ionizes, it goes to zero. That's precisely what we might see. One trough from pre-Dwan era, one peak during reionization, and zero. But suppose we did not have much X-ray heating. What is possible is that a trough can go into another trough. Because I haven't heated the medium, but laminar alpha mixing has pushed TS close to matter temperature again. And if that happens, then I may have another trough. And that's precisely what I'm seeing here, another trough. But it will rise again as the heating takes off. The signal would be seen in emission and finally go to zero. In the next few graphs, I show you a whole range of such models, right? So there is this trough close to frequency of 20. This is universal. This cannot be changed based on reionization model. Reionization model lead to a complicated set of models. It can lead to sharp absorption. There may be no absorption. You can see signal in emission. So you see all of these range of models are entirely possible. And all that, this paper that I'm giving, this is from my own paper in 2005. Now, all that has changed is that this entire thing has shifted to larger frequencies. So this entire game would shift to around redshift of 80. That's all that there is, from 60 to 80, not much more. And this will go to around, instead of 120, 130, it'll go to around 180. But physics is the same. All of these models are possible. So our aim, as far as detection is concerned, is to figure out which of these models is preferred. Whether there was another trough when reionization started because there was not much heating, or one rose from here and went into emission, reached some kind of peak signal and then tapered off. You are going to hear talks on radio astronomy, and so I will not actually spend much time on what is observable and what is not observable, because you'll already hear that the whole of next week you'll be going spending time on this. My point is to just underline that this entire set of models are possible. Here is a cartoon picture of what you might see, and you can see the cartoon picture tells you there is one trough around minus 50 millikelvin. You may have another trough before heating happens, and this trough might be deeper, and I'll come back to that point. Then heating begins, the gas goes to emission, and then reionization ends. So you see the only difference between this curve and the one I showed you was everything is shifted slightly to the right. So this is what we expect. One trough from pre-dawn era, one trough from beginning of reionization, what is called cosmic dawn. So this trough corresponds to firmly in the era of cosmic dawn. And then epoch of reionization, when the signal is observable in emission. But something changed this entire scenario a few years ago, and that's what I'm going to discuss next and finish my talk with. It is what's called edges detection. Edge is an experiment that is working in a frequency range between roughly 50 and 100. You can see the frequency range it's working in. And what they found a steep absorption trough. You pay attention to the right-hand side, the lowest right figure, and that is their final process spectrum. The others are spectra at different form. The top A corresponds to the background temperature expected at this frequency. So we have to tell something which is around 500 millikelvin from a sky which is around a few thousand degrees. It's always a hard thing to say. Then in B and C, they have discussed different kind of RMSs and signals that they have got on their different runs. Figure D is a neat figure actually, which is based on E. But what E shows, figure E shows the right hand side, is that there is a trough. between frequency of roughly 70 to 90. There is a trough. What is even more notable is that this trough has a depth of around minus 500 millikelvin. That was that expected at all? It is a deeper trough than any one of us had expected based on any model that one could construct. And it lasts, if you convert this into redshifted H1 line, between roughly redshift of 19 to roughly redshift of 15. So between redshift of 15, and so if you interpret this as coming from the cosmic dawn era, then we are seeing a steep trough, very deep trough actually, in a redshift range between between 19 and 15. Before I come to this model, I will just summarize it and we'll come to models later on. So this is a 500 millikelvin absorption trough in a frequency range 70 to 90 megahertz, corresponding roughly to a redshift of 15 and 19. That's what it is. It is completely unexpected that because we could not have got this kind of an absorption trough, even for a fully unheated gas and Lyman alpha coupled gas. Lyman alpha coupled gas will couple it back to matter temperature, right? That's what is needed. Matter, remember, is CMB is hotter than matter at this redshift, something I've discussed in last few classes. So maximum depth of the trough was not expected to be more than 200 millikelvin. This was 500 millikelvin. So we already have a problem. You may wonder, in astronomy, factors of 2, are they such a big problem really? I mean, the point is we are always within a factor of 2 of something. So is it a problem that the maximum trough was expected to be 200 millikelvin and what we have found is 500 millikelvin? Yes, there is a problem because here we are connecting to that part of cosmology, which is incredibly precise, we are linking ourselves to precision cosmology. In rest of modeling, it is always possible to get these factors. Here, how will I get this factor? Can I decrease ionization fraction? I showed you a figure day before yesterday. By decreasing ionization fraction, I can cool it more because the decoupling happens earlier. This depends only on the recombination coefficient, and I can't do that actually. I can make models, but I cannot have a physical model to decrease ionization level and thereby decreasing matter temperature as compared to CMB temperature. Can I increase baryon fraction? No way. This is strongly constrained by CMB anisotropies. I can't do that also. Can I do something about reionization in thermal history? Well, recombination history almost impossible to change because it's extremely well constrained by CMB anisotropy bounds. So this is not possible. I cannot make 200 millikelvin, 500 millikelvin by any physical processes known to me. And those physical processes are extremely well constrained from CMB anisotropy measurements. I mean, at least if we extrapolate them to smaller values. I mean, if I study recombination and I have a curve that extends to small level of fractional ionization, I have to believe in that, right? Unless I invoke another process at that point, which is not easy. But this also gives you an opportunity, right? Is there new physics? Already there is a question, there were discussion we had right in the beginning about additional dark matter baryon coupling. So it is possible that there is more dark, we know that by mass there is more dark matter, but if dark matter was cooler than baryons and the number density of dark matter, the number of dark matter was more actually, number density of dark matter particles is not known to us. So we have a heat bath which is cooler than baryons, so it can cool them. So we can actually cool baryons by dark matter baryon coupling. We can actually inject energy into the radio at around redshift of 20. Something I've worked on, I'll show you just one view graph actually. It is possible that we are all completely on the wrong track. It is interstellar medium dust. Some people have written papers on it. Not easy to do that. And it could well be an instrumental error. Something which people have looked at and there are always issues being discussed. Now I will show you this plot. How well can we model edges detection? These are all range of models. FL actually parameter which is plotted here corresponds to how well you mix using Lyman alpha. So let's look at F1 equal to 1 model. You see, it is possible that the signal is very close to 0 in that case because if you don't couple Lyman alpha to the gas, remember, your signal is expected to be close to 0. And that's what this first model shows. The red curve is way off in the top. And these 3 different curves for red correspond to different heating histories. So you heat differently, but you still do not get much of a signal if you do not couple using Lyman alpha well. You have to couple using Lyman alpha well. But there are a whole range of other models. You couple Lyman alpha very early and you do not heat the gas. So this is the kind of model you may get. You have this that black curve, but you do not go below 200 millikelvin. I told you 200 millikelvin is about the maximum you can go. Whatever model you make, I can make tens of different models. I cannot go below minus 200 roughly, because the simple reason that it's the ionization and thermal history of the background that limits it. My models will always be in this range. I can make models of different Lyman alpha coupling, different heating histories, but edges I will not reach. That's the point I was trying to make. It probably is an opportunity for us to explore other set of models, dark matter coupling, energy injection in early universe. And that's what it is. And this figure actually gives you a sense that it's not possible to model it using the usual physics we do. Janki will discuss some of these things with you in greater detail later on. Now I'm going to come towards the end of my lecture. I'm also running out of time. So it's possible to actually, like I said, like can do a few things to explain edges result. You can couple dark matter to baryons, or you can inject energy. Remember, if you go back to this equation, and I'll show you back this equation 25. I can raise TCMB, I can add to CMB something else, and that can make the absorption trough. So I can either decrease TS. TS is coupled to matter temperature. So if I decrease matter temperature by cooling baryons, this number will increase. Or I can either decrease the denominator or I can increase the numerator. So here I say, okay, why don't you increase the numerator? And that is just one model, and very briefly I'll discuss with you, which is being envisaged here. So what you do is, XE is 10 to the power. So this faint dotted lines you can see here, vertical lines. This is the range in which we need to pump energy to satisfy edges result. And what is plotted on the y-axis is the ratio of distribution function in the equilibrium to the distribution function that is injected. So you inject additional photons and energy at very low frequencies in CMB, and you study the evolution of the distribution function. So this is how the distribution function looks like at one redshift, and you let it evolve. Most of these photons are absorbed by free absorption, and the bottom curve is what remains. This is one of the models which might be allowed. I mean, it may not be, because here it is still close to 1, but slightly larger than 1. We need a factor of around 2.5. So this model is roughly about okay. So what is possible is you pump in a lot of energy in the pre-recombination era, and most of those photons get absorbed, but they are detectable as spectral distortion of CMB. That was the reason we actually worked on this problem. That if you try to explain edges by energy injection in pre-recombination era, it's actually detectable by next set of spectral distortion experiments. So yes, edges detection has given us an opportunity to explore different models, but maybe that detection either will not be minus 500, then more usual models will suffice to explain it. But still, we have now got our feet in one very specific era in the universe where it appears there is a signal, and we may be able to study it and say something about both thermal and ionization history of the universe. This was my last view graph, and I'll just end with future perspectives. So our current understanding of cosmic dawn, epoch of reionization, arises from two observations. Planck result, which I did not discuss at all, but you have already heard about it and you'll hear it again. That fixed the epoch of reionization to around redshift of 8. So that is redshift of 8, and edges result that put strong constraints on physical process during the era of cosmic dawn, between redshift of 15 and 20. Right? That's where edges works. So the best probe of cosmic dawn might be redshifted H1 line, and edges result is indicating that. And there are ongoing efforts and planned experiments to detect both the global and the fluctuating component of the signal. I only discuss the global signal. Janki will discuss fluctuating component of the signal later today in one of the tutorials, because I did not have time to talk about fluctuating component of the signal. So some of these experiments are working on the global part, and the other experiment, most of them are looking at the fluctuating component of the signal. And SK, which is towards the end, is something which is being planned right now. In many of you, the students who are hearing this might end up working in SK and might look at this problem and the data in 6 to 7 years' time, and might be able to address this question more directly with data, which is not possible except a single result from edges. There may be other lines actually. Hyperfine line, I may briefly mentioned it, like singly ionized helium-3. I've worked on this a bit. And this might play a role, even though it is actually the signal is even weaker than H1. But its advantage is that the frequency is higher, and generally radio astronomy is easier at higher frequencies than at lower frequencies. So frequencies, factor of 7 higher frequency means your foreground is weaker by almost 2 orders of magnitude. So the 2 orders of magnitude loss in the signal is gained by 2 orders of magnitude in the foreground itself. So this might play a role, but I'll not say anything further. And I think I have run out of time, and I will stop now and take questions. Thank you.
I just have one question about the possibility of baryon and dark matter
Sorry, please go
coupling.
on.
What I am talking about is the possibility about coupling between dark matter and the baryons.
Go on.
So you are saying we can cool the baryons through coupling,
Mhm.
and baryons are quite relativistic in the early universe, and we are
Baryons are
we are
what? Sorry,
taking
say it
dark
again.
matter. Hello,
Baryons are
can you?
what?
Baryons are quite relativistic, right? And
They are not
we are taking
relativistic.
dark,
They're
but
not relative. They are completely non-relativistic.
we take pressure of the baryons for some of the calculation, right?
Yeah, but pressure is a non-relativistic gas. We discussed it. A baryon is a proton. A proton has a mass of 930 billion electron volt.
Yes,
The
sir, but
temperature of the gas
it
is a few
corresponds
electron volt.
to warm matter, right?
Huh?
And dark matter is a cold dark matter, right? In our
It's correct.
model.
Dark matter is cold.
So the dark matter particles have a large mass, and through coupling, we are just saying that baryons can collide with the dark matter.
That's correct.
So, but they do not collide in our general models, right? So, which force is responsible for it? It is not gravity, but
Well,
uh,
it is possible that, so one class of models I've also studied. One class of models which are possible are what are called milli-charged particles. So the interaction is actually electromagnetic. So that what you think is dark matter is not entirely dark. It has a milli-charge. So milli-charge models, it can have a charge of 10 to the power minus 6 times the electronic charge. So the
okay, sir.
interaction, in fact, it has to be Rutherford kind of scattering for these models to work, because the scattering has to be, cross section has to be stronger at smaller temperature. And Rutherford scattering is 1 by V4. So most likely if this kind of a thing happens, it can only happen if it is some kind of Rutherford scattering. And the most natural model for Rutherford scattering is a milli-charged particle. A particle has a small charge, 10 power minus 6 to 10 power minus 7 times the charge, electronic charge. So it is plain and simple electromagnetic interaction between charged particles, protons, and dark matter particles. Yeah, that's the most natural model.
And also then we can also add one more term for the dark matter collision, right?
That is correct.
In the same form.
That is correct.
Maybe coupling would be different. Okay.
No, it will be the same coupling. See, once you charge particles, you cannot avoid that coupling term.
Yes, sir.
So you see, once you do one, you cannot avoid the other, right? But you remember the cross section.
But strength of the coupling, what
Weaker.
time the total strength, right?
Because you see, dark matter itself has electronic charge of 10 power minus 6 to 10 power minus 7, right? So the coupling interaction, the coupling between proton and that is stronger than the coupling between dark matter and dark matter, right? Because they're both at.
So that charge limit is experimentally defined, or
Yes, it is defined based on CMB anisotropies actually. And those are the typical numbers I'm giving you. So if you want to satisfy CMB anisotropies bound, your charge on the particle cannot be more than around 10 power minus, either 10 power minus 6 or 10 power minus 7. By the way, it depends on the mass of the particle also. It doesn't
But
depend.
sir, if we are considering also charge on the dark matter particle, then
Correct.
it can also collapse like galaxy, right? It
Well,
it
well,
will not form a halo.
it is,
After the halo
whether it will
formation,
form a halo or
it
not
can flatten
has to
out.
be satisfied, right? Yep.
Yes, sir.
So
Okay.
those things have to be studied, you see. So the point is, I can refer you to a paper of mine where I discussed it, that the halo has to remain a halo, right? Otherwise, the halo itself will collapse.
Yes, sir. Yeah.
So yes, so the loss of energy for such milli-charged particle is not so large actually. It's larger than expansion rate of the universe at the present, at the kind of typical densities. But fact of the matter is, there are all kinds of difficulties in such models. So in principle, if you have a mass of around few million electron volt, and if you charge around 10 power minus 7, it can be a fraction of the dark matter. It cannot be all of dark matter. But that fraction suffices to cool the baryons. That's also true.
So we
So,
can also consider the warm dark matter and cold dark matter together,
I
right?
mean, that doesn't matter for
Fraction.
this coupling.
Yeah.
Warm or cold will not matter for this coupling. We generally, when we consider this coupling, we take a cold dark matter model, right?
Yes, sir.
So yeah, we can take a warm dark matter model, but for this coupling, it will not make so much of a difference. Well, it actually,
Okay, sir. Thank you.
velocity dispersion could be non-zero. It will make some difference. All right. Okay. We can discuss
Yes,
it further
thank
at some, I mean, over email or something if you have some more doubts. I mean,
So,
please.
Okay, sir. Thank you.
Yeah. So if the edges result is correct, can it rule out the models of X-ray heating?
What models?
Some of the models for X-ray heating, because X-ray heating can produce such a deep or not.
Sure, sure, absolutely. You have to look if X-ray heating, some of the models which are shown here, like green curves or whatever
Yes.
curves, like I
Mhm.
mean, those extreme models, like yeah, of course, like for instance, this dark line,
Hmm.
right? Now, well, this is ruled out, isn't it?
Yes, exactly.
Because point is, if I heat too early,
Correct.
right, then I have a problem. Because
Yes.
by the time you come to redshift of 15, you're already in emission, right?
You're right. Exactly.
So yeah, a whole range of models are ruled out by
Correct.
this process, right? It
Yes.
affects many class of models.
Yeah, and you mentioned that some of the models can, some of the exotic models can say something about the edges result, whether it's they can reproduce, but they can produce the flatness as well.
Flatness is a problem. Flatness is not easy. By the way, flatness, in my view, when I look at this,
Yeah,
is an
exactly.
artifact of the detection process itself.
Ah, okay.
It is not likely to be as flat it is. It's actually like they are not able to distinguish a line from a flat curve, actually. So even
Correct.
I think they, even in their papers, they don't really push for it.
Right.
Most likely, it is what I have shown here in the
Okay.
blue curve. Dot that is blue curve.
Correct.
It will be
Okay.
something like this. This will be
Hmm.
the reality of the
Correct.
detection.
Yes.
Because when you look at the detection paper, right,
Mhm. Hmm.
if these were experimental points, like you have to put points with error bars here,
Exactly. Correct. Correct.
it's not the case.
Mhm.
So this trough is an artifact of, it's real, but it's an artifact of the way the observation data is analyzed.
Oh, okay. Correct.
Reality is probably more like this.
Right.
I'm not saying the trough is minus 500, so you still have to explain it. That's not the point.
Mhm.
The way it rises and the way it falls is not as flat as shown here.
Right.
More likely, this is the reality of edges.
Mhm. And do the edges have a frequency coverage that can show the emission as well?
Oh yeah, no, edges doesn't have.
Doesn't have. Okay.
No, you can see this is the
Right.
coverage.
Right. Right. Okay. That this is much okay. Hmm.
Well, they can show there is a rise and fall, something like that, but you can't show the rise beyond it. These points
Correct.
are not, no, it can't show the. It doesn't have that coverage.
And what about the Saras?
Well, I suppose.
I have a short question regarding this.
Go on. Who do I answer?
Prakash, please go ahead. I'll just
Yeah,
ask.
so
I was just curious, what are the status of
coverage.
Saras? Whether
Well,
there are any.
it has more coverage. It can
Uh-huh.
go to higher frequencies, 120, 140.
Ah, right, right.
Yeah.
And are there any, data? I mean, the
There
results.
is some data they are trying to publish actually, but I do not know details of that.
Okay, okay, yeah, sure.
So what I'm going to ask is that what are the dot line, dash line, and the solid lines denote here?
Here, so point is for every Lyman alpha cup mixing model, there are 3 heating models.
Yeah, yeah.
That's the line.
So what corresponds to what?
So the whole point is, if you take FL, the red line FL equal to 1 is red. All the 3 red curves correspond to FL equal to 1, but correspond to 3 different heating models.
Yeah, I'm just asking what different heating model denotes is denoted by what? Like so, dot lines are for what?
Dotted lines are for weaker heating models. You can see the trough is deeper in those cases. Let's look at the solid
Okay.
line. Black line. There is
Yeah.
a solid black
Yeah.
line, there is a dashed black line, and there is a dotted black line, right?
Yeah.
The dotted black line is less heating as compared to the solid heating, solid line. You can see it. Solid line heats fast and goes into emission very quickly.
No, that I understand. But so what is the difference in between these 3 plots? Like what? So there is certainly there is a change in the value in some parameter or something like that. So what is that? So what is different in these
I
3
don't know.
plots?
I mean, the whole point is
Shiv,
that these are 3
can I
different
answer
heating models.
this?
Janki can answer this. Go on.
Yeah, so this is just basically number of X-ray photons which are emitted from the sources, and they are falling by factor of 10, I think, in this. So
Factor of 10. Okay.
yeah,
Okay.
so that's
I don't remember
basically
offhand actually what the number.
number of this is basically just number of X-ray photons which are emitted, and the spectra is the same for all 3 curves.
Okay. Okay. I understand.
So
Thank you.
one can consider a whole range of models, right? That's why one actually forgets what exact model one has taken, right?
Yeah. Sure.
So here it's only the number. You can, I think we had some figures with the different spectrum also, right, Janki? Didn't we in our paper?
We had, but we had
We
that,
showed
but
that.
most of the effects of the spectra, I mean, if the spectrum is not drastically
That's correct.
changing, can be also kind of degenerate with the number of X-ray
That is correct.
photons.
You can cover probably some of those models in greater detail. I just wanted to show one figure actually. I mean,
Okay.
yeah, I didn't want to show, but maybe you can discuss it later on. I mean, in greater detail.
Okay.
Are
So
there any
does
further
this,
questions?
yeah, does this edges result also say something about the structure formation that it should have started very early?
Not really. You
Not
see,
really.
the point is edges result. If you look at this, it says one thing actually.
Mhm.
Lyman alpha coupling should have been finished around this redshift of 19.
Correct.
Now that is a very important thing. And strong heating must have started around redshift of 15,
Right.
right? So
Yes.
these 2 things are saying something about structure formation, right?
Mhm. Correct.
You can see, in fact, the best curve to look at it is the like red curve, right? Red FL equal to 1, red curve, solid curve. There is nothing there. Why is there nothing there? Because Lyman alpha coupling hasn't happened. Without Lyman alpha coupling, I see nothing in emission or absorption, pretty much, right?
Correct.
So to get something so deep, first of all, we have to couple Lyman alpha very strongly.
Yes.
And you can see the clear trend here in these curves, right?
Right.
Lyman alpha coupling has to be strong. It must completely couple the gas to matter temperature, which is low at around redshift of 19.
Right.
Heating must happen before redshift of 15. I mean,
Right.
start that. So these 2 parts of the curve what implication it had for structure formation? Of course, it has formation. And for some reason, ionization is not strong,
Right.
right? Because we are seeing most of the gas which is still neutral, right?
Right.
So yeah, so it is actually saying something about structure formation. What exactly it is saying, I don't want to speculate that. Actually,
Correct. Correct.
fairly from all the models that we worked on for this paper,
Mhm.
we do not hit a physical limit for structure formation, right?
Yes.
Physical limit would be something is not possible. All of
Right.
them are possible, these models,
Correct. Correct.
right? So I will not go out and say, okay, it is saying something about formation of structures is early. Redshift
Yes.
of 30, if you start forming structure, all of these are possible models.
Right. That's right.
So they are not
Yeah.
ruled out by any other principle. Except for, I mean, these are only difference in models like in X-ray. X-ray emission is almost completely unknown to us from that redshift.
Yes, that's right.
Right? So we can actually change by a factor of 100 roughly.
Right.
Because that happens from binary stars. We don't know whether binaries even form in those structures, right?
Correct.
So yeah, that is uncertain.
Yeah. Thank you.
Any further questions or? I think we have gone on for long. So I'll stop and Janki will take over from here, right?
Yeah. So let us close your 3 lecture session here. And thank you, Shiv, for this excellent set of lectures.
Thanks a lot. Yeah.
I'll clap with my virtual hand here.
Yeah.
And so to the participants, if you have any questions or comments, you can redirect it to Janki, us, or you can directly write to Shiv.
Yeah.
And you will be responded properly. Okay, so thank you, Shiv. Now Janki will take over from Shiv and discuss the details of the calculations that has been discussed earlier.
Thank you. Thank you, everybody.
Over to you, Janki.
Bye-bye.
Yeah. Thank you.